magnetic impurities have this ferromagnetic ordering. Of course, when those magnetic polarizons overlap with each other, that's how we get this long-range magnetic order. Of course, below some population threshold, the system remains, semiconducting or insulated. So this seems to be a very sophisticated and convincing model, but it was proposed decades ago. But I don't see any convincing, quantum mechanical result to confirm this model. So I decided to do some systematic investigations. So there's some very heavy calculations of 4x4x4 supercell. I have two ion atoms in this 4x4x4 supercell, and those ion atoms are fully coordinated. Of course, I fully relax atomic positions with both anti-ferromagnetic and ferromagnetic ordering respectively. And this is the main results. I mean, it shows the anti-difference between those two magnetic states as a function of ion distance. So yes, when the ion atoms are right next to each other, ferromagnetic ordering is favored, but this ion-ion coupling strength quickly decays to zero basically beyond the next nearest neighbor. So clearly there's no long-range coupling, at least at the level of LDA. Then what we have if we introduce oxygen vacancy, the present oxygen vacancy changes the story completely, but make my situation even worse. That is, the present oxygen vacancy actually makes the anti-ferromagnetic states more stable. In this configuration, actually, this oxygen vacancy is actually kind of far away from this ion dimer, but still, it makes the anti-ferromagnetic state energetically more favored. But in this configuration, those two ion atoms are kind of far away from each other, and there's an oxygen vacancy in between, very much like this magnetic polarization model presented in that Nature Material paper. But because those two ion atoms are so far away from each other, those two magnetic states essentially have the same energy. So again, the present oxygen vacancy didn't introduce any long-range coupling. So during my exploration, I find something quite interesting. I'm not exactly sure whether this is relevant to the bigger problem in this long-range magnetic order, but I think it's very interesting and worth mentioning. That is, when I look at this root 2 by H supercell, the bar polarization is along this long axis. These two ion atoms, of course, are very far away from each other. The distance is about like 16 angstrom. What I find is, this ferromagnetic state. That means the total magnetization is non-zero. It has the same energy as the ferromagnetic state. Of course, I can constrain the total magnetization to be zero, but this non-magnetic state has much higher energy. So there are two things from this calculation. First, again, there's no long-range spin coupling because these two magnetic states have identical energy. So it doesn't care about whether those two spins are parallel or anti-parallel. But somehow the magnetic state overall has lower energy. So the question is, what makes these two ion atoms sort of different in this ferromagnetic state? I did some structural analysis. It turns out that in this optimized structure, the presence of ion dopants create some weakly charged domain walls. So if you look at, so what I showed here is the atomic displacement along the Z direction. So this ion 2 is essentially at the tail-to-tail domain wall, and ion 1 is essentially at the head-to-head domain wall. So I think there are two competing factors here. So remember, these ion atoms are fully coordinated, so I'm forcing it to be 4+. Ion really doesn't want to be 4+, so there's some energy penalty here. But meanwhile, the dopant will try to match the oxidation state of the replaced ion in that, so to avoid the formation of charged interface. So I think we have two competing energy terms, but in this case, the formation of charged interface is slightly favored. So making these two ion atoms slightly, local environment is slightly different. I also look at layer resolved density states. Again, so overall, the system is insulating, but if you look at those two domain walls, they're slightly conductive. We see localized holes. They're actually most coming from the oxygen atoms, and here the band structures, the states crossing the Fermi energy. Again, those states they're very p orbital-like. They're coming from oxygen atoms near the ion atoms. I then look at, another superset. I just want to see the formation of charge domain, or whether it's an artifact or not. So in this case, the ion-ion connection is perpendicular to the bark polarization. So the bark polarization along z direction. So, but in the optimized structure, still I see the formation of weakly charged domain walls, and the main message is more or less the same. I see the ferromagnetic state and ferromagnetic state have similar energy, but the magnetic states have lower energy than the non-magnetic state. So I think with this DFT calculations, we do learn a few things. That is, there's no long-range coupling, and the magnetic-polar model, at least at level LGA, doesn't seem quite work. So I have to end this with a big open question: is how relevant is this domain will induce the ferromagnetic state? We probably have to think about the possibility of ion clustering. So with this, I would like to end my presentation. I think even for some simple system like ion invariant tunneling is not simple at all. I think a systematic study, both experimentally and computationally, is definitely required. And thank you for your attention.
Thank you for a great talk. So, in the case that you mentioned that iron doesn't really want to be 4+, do you think that the different polarization pointing away from iron, I think that's the way that you showed it, help it to be in its favorable oxidation state? Because I would think that iron might like to be like the 3+, so it might want to get more electrons, so polarization actually pointing toward it might go into the electron. But the way that you showed it, it was pointing away from it. So I would kind of get a feeling that it might be
yeah, so remember we're using purely boundary conditions. So yes, one ion, they have polarization pointing toward it, but because of the setup, the model, whenever create a head-to-head domain, it will be coupled with a tail-to-tail domain. So again, this ferromagnetic state is very interesting, but at this point, I'm not 100% sure how relevant it is to this bigger question, this long-range magnetic artery observed experimentally. So this,
but indeed, the charge of the two ions is different, right?
Yeah, they're slightly different. You can tell from their local magnetic moments, they're not the same.
Question?
Yeah, so in the first part of the talk with your defect dipoles, there's a kind of natural mechanism for generating defect dipoles in lead, at least in lead titanate,
Yeah.
with the lead oxygen divacancies that's been studied off and on over the years. So I mean, are you thinking that could be the dipolar defect, or you have another origin for your dipolar defects?
We are most focused on the dipolar defects, the B side, like Doller acceptor dopants like manganese, iron. So for manganese, if you replace titanium, to compensate the charge, you need oxygen vacancy. There you get a dipolar defect. So Ron has some papers about manganese dipolar defect as well. So I think our model most focuses on like dipolar defects, sort of originate from B side, not A side.
But you can get the same thing on the A side. I mean, but then it's a little harder to control.
Yeah, because the A side dipolar defect is not exactly along the polar axis, so there may be some subtle difference.
So for that case, where you have the B-side dopant